Okay, today we discuss a different type of sensor, still based on micro electromechanical systems, and in particular we talk about MEMS gyroscopes. The gyroscopes are an instrument capable to measure the orientation in space in 3 dimensions, or the rotation with respect to an absolute directions of the mounting of the package. Okay, so they measure the orientation in space in 3 dimensions. And therefore are typically used for navigation. This is basically the first historical use of gyroscopes. Navigation, especially when the Earth magnetic field, the geomagnetic field is not usable. For example, in space, or in tunnels, or in where the geomagnetic field is disturbed. Okay, when the geomagnetic space, on a plane, in a tunnel. These are the typical situations in which, in order to know the through direction of the vehicle, it's important to use the gyroscopes. Okay? In typical conditions in sea navigation, for example, one can use a compass, la bussola, which uses the geomagnetic field, but of course in space on a plane this is actually not usable. But navigation is also, the gyroscopes are also used for more common uses, for example stabilization. For example, in the stabilization of the cameras, one corrects the position and the photographs on the basis of the measurement of the gyroscope, and for robotics. In order to know the exact orientation of a robotic arm, for example, typically a gyroscope is used. So, now I want to focus on a specific type of gyroscopes, because historically gyroscopes have been developed in the 18th century, and they were let's say large instruments with metal ball, metal rotating discs. Of course, this is interesting from the point of view of the history of instruments, but practical and recent gyroscopes are typically fabricated with the so-called MEMS technology, which is a technology that uses the silicon fabrication technology. A gyroscope is usually, as of now, sold in the same package as a MEMS accelerometer. Typically one has a single package which is called the 6-axis accelerometer and gyroscopes, which means that we have a 3D accelerometer plus a 3D gyroscopes in the same chip. SOP, which stands for System on Package. This means a 3D accelerometer, plus a 3D gyroscope. The acronym SOP stands for System on Package, and means that in the same package we can have different dies with different functions. If you remember the video that I've shown you the day before yesterday with the accelerometer, we had a MEMS accelerometer, the mechanical part, in the package, and on a separate die we had the electronics. Okay, and typically for these 6-axis accelerometers and gyroscopes, we have a single die with the 3D accelerometer, a different die with the 3D gyroscope, and a third die with the electronics, all in the same package. In that case, we say we have a system on package, because we have a complete system with different integrated circuits in the same chip, in the same package. Okay, for today we focus on how this MEMS gyroscope operate, what is the physical principle of operation, and in very, very simple terms, how it is done. Okay. The physical principle that is used in a gyroscope is the conservation of angular momentum. It's a very basic physical law. This is a basic energy conservation of angular momentum. It's a very basic conservation law of mechanics, which says essentially that the total angular momentum, the total of a system with respect to a fixed point is constant if no external force acts on the system. So basically it is the same law regarding the conservation of the total momentum della quantità di moto if no forces act on the system, this time for the angular momentum instead of the let's say general momentum. So when we want to use and exploit this property in a solid state gyroscope, we need to use the conservation of the angular momentum acting on a vibrating mass. Because instead of having something which rotates in a solid state gyroscope, we can have something that vibrates. Okay, so this is the main difference with respect to the traditional 18th century gyroscopes. We have no rotating disks, no rotating masses, but we have some vibrations. We have a vibrating mass, and the vibration is going to be very, very small, because in a situation which is similar to what we have seen in the case of the accelerometers, the vibration around the normal position of the masses is of the order of 10 microns. It's a very, very small vibration, fast but very small vibration around the normal position. And on the vibrating mass, we see the conservation of total angular momentum as a manifestation of the Coriolis force. So let me just explain what is the Coriolis force with a few examples. So first of all, the Coriolis force is a consequence of the conservation of angular momentum, and is what is called an inertial force. In inertial force in Italian means una forza apparente that we see in a reference system which is rotating with respect to a fixed reference system. Okay. Now, I don't want to use too many formulas here, so I will just show you an example of this Coriolis force, how it appears in a rotating system. And, for example, let us assume that this whiteboard is a fixed reference system, and in it we have a rotating reference system. Let us assume that this is the reference system. This is an object in the rotating reference system. So if time goes in this direction, we can have, for example, 3 snapshots. Let us assume that this is rotating in this direction. Okay, let's call omega the angular velocity. Then after some time this is in this direction, and then after some time it is rotating some more. Okay, so we have three separate snapshots, and let us assume that we have a mass in this square which is not subject to any force. So according to Newton's law, this mass is moving along a line with constant velocity. Okay, let us assume that the mass is going in this direction with this velocity. So at some point it is here, then it is, well, let me draw it in another position, in the center, because it's easy to. So it is here, okay? Then the situation, it would be here. And then let us assume that this is fixed. So this is fixed, and this is fixed. It is gone, let's say here. Okay? So with respect to the fixed point, the mass has just moved along a vertical line with constant velocity. Okay? Because of course there is no force acting on the mass. Okay? However, if we look at the trajectory of the mass from the point of view of the rotating reference system, we see that the mass is on a completely different trajectory. So let me draw it again with respect to the rotating reference system. So I start with the same position here. So first position, the mass is here. In the second snapshot, I consider this square fixed because I am now on the rotating system. So I see the system exactly in the same position. But now I see the mass in, let's say, in this position. Okay, so it was here. Now it has gone in this position. And then if I plot the third snapshot here, again, this is the fixed point, I see the mass now here. So if I plot also the previous positions, what I see is not a mass which is moving in a I do not see a mass which is moving in a linear direction with constant velocity, but I see the mass on a curved trajectory. Okay? And what I see is that it has an apparent velocity in this direction, then in this direction. But of course, if the trajectory is circular, what I see is a force acting on the mass perpendicular to the trajectory, which gives a curved line. Okay? And this is the Coriolis force. Okay, you see, from the point of view of the rotating system, it is as if there is a force acting perpendicularly to the velocity on the moving mass. And this is the reason why it appears that the mass has a circular trajectory. Okay? Now, so as you can see, it is completely apparent because there is no actual force on the mass. Okay? With respect to an absolute reference system, the mass is only moving linearly. Okay. This is just for those of you that never heard of the Coriolis Force. Now, we can write an analytical expression of the Coriolis Force, and as you can imagine, it depends on the velocity of the object, and it depends on the angular velocity of the reference system. And the expression is the following one. AC, the acceleration due to the Coriolis force, is equal to 2 times the vector product of the velocity and of the angular velocity. So, this, of course, is also what we have shown on the example, because the vector of the angular velocity is perpendicular to the whiteboard. The velocity is in red, and the green line, the Coriolis force, is perpendicular to both the velocity and the angular velocity vector. This is the Coriolis. Of course, this is an acceleration. Because Coriolis acceleration, the force is just the acceleration times the mass. Acceleration. Okay? Now, how do we use it in order to measure the orientation? Of course, where do we have the information on the orientation of the reference system? It is in omega, because we know we have that this acceleration is proportional to the angular velocity, so that we can, from the angular velocity, have some information on the rotation of the reference system. So, let's look at how we exploit this phenomenon. Typically what we have is a reference system which is rotating, for example, with an angular velocity omega in this direction. And in order to exploit the Coriolis force, we need to have two vibrating masses, two equal vibrating masses, M, which vibrate in opposite direction along this line. So at a given time they are moving in opposite directions, so they're moving in this way. Okay? We need some actuators that let this mass vibrate. So, if we exploit the Coriolis force, what do we have? Of course, you remember that the acceleration is equal to 2 times v vector omega. And so, for example, for this mass, for this one, we have that v is in this direction, omega is out of the whiteboard, and therefore the acceleration, the Coriolis force, is up. So we have a Coriolis force in the top direction. Let me use a different color. So we have the force is just the mass times the acceleration. Okay. The other mass, of course, is subject to a Coriolis force in the opposite direction, because we have the velocity which is reversed. The angular velocity is in the same direction, and if I use the rule of the right hand, I have V, omega, and F to the bottom. Okay? Now, this is it. Because just by drawing this, we can, after we draw this, we can use what we already know. Because if you remember the operation of an accelerometer, in an accelerometer we measure an acceleration. Okay? How do we do that? We transform an acceleration into a displacement into a variation of capacitance, and the capacitance, a variation of capacitance into an electrical signal. This is what we saw on Wednesday. And here it is the same. We have an acceleration, so we want to measure the angular velocity. We transform the angular velocity in an acceleration, this Coriolis acceleration, and then we can transform the acceleration into a displacement by using a mass, a spring, and a damping. Then we can transform the displacement into a variation of capacitance, and it's done. And from the variation of capacitance, we can have the electrical signal. So, for example, what we do here, we can use this mass as the moving plate of a capacitor, if this mass is connected to a spring, as in an accelerometer, and then we can have a fixed plate here, and therefore we have a capacitance C1. Okay? And similarly, we can use the other mass as the moving plate of a capacitor, and we can have a fixed plate here and measure the variation of capacitance C2. Okay? So, again, if the whole housing of the system rotates, the two masses are subject to a Coriolis force in opposite direction. This Coriolis force is transformed into a displacement in opposite directions of the two masses, and what we observe is a variation in opposite direction of the two capacitances C1 and C2. Okay? So, in essence, it is very similar to what we have seen for an accelerometer. The technology is the same. If you look at a picture of a gyroscope and at a picture of an accelerometer, I mean, it requires an expert eye to recognize which is which, and because let's say the underlying type of operation is very, very similar. Now, the question is, why do we have to use two masses? Okay, but you have to think that since the mechanism of operation is very similar, you can have in the same system both a rotation and an acceleration. Okay, why do we have two masses? Because assume that you do not have a rotation, but you only have an acceleration of the package. Okay, if you have an acceleration, you have a displacement, and you measure a variation of the two capacitances. Okay? But if there is an acceleration, the displacement of the two masses is in the same direction, and therefore the variation of the capacitances C1 and C2 are in the same direction. Okay? Instead, if you have a rotation, the two capacitances vary in opposite direction. So you need two capacitances in order to distinguish if you have an acceleration of the whole package, because in that case you simply have an increase or a decrease of both capacitances, or if you have a rotation, because if you have a rotation, you have that, for example, one capacitance increases and the other one decreases. Okay? So we cannot use just one mass, because with just one mass we would not be able to distinguish between an acceleration of the whole system or a rotation. We need two masses, because with two masses we can look at the difference between C1 and C2. And if there is an acceleration, they both increase, so the difference remains 0. If there is a rotation, you see a difference, which is finite. Okay? So we need to measure C1 minus C2, because that is proportional to omega. Let me write here, if there is a linear acceleration, C1 and C2 vary in the same direction, and therefore C1 minus C2 is 0. Okay? And also, this is also the reason why we choose an exactly symmetrical structure, so that the two masses are identical and the two capacitances are identical, so that the difference is exactly 0 if they're subject to the same linear acceleration. Okay? Now, let me show you some animation, because it's probably, I think it is easier to understand when I draw the thing very slowly, because you see the minimum number of things that are required to understand how it is working. Now I can show you some richer animation, which I think it's clear if you have understood the operation. Otherwise, it can become a little bit confusing. But let me show it to you. So, now, this is first an animation of the Coriolis effect. Just, this is funny, so you can just, okay, I have no sound. Okay, this is funny actually. It's nice. Yeah, well, maybe it does not need any explanation. It's pretty easy. Okay, they are launching a ball, and you see at the moment they are in a fixed reference system, but then the thing can start rotating. No, it's just fun. Okay, simply if they launch the ball linearly, there is this apparent force, of course, and the ball gets moving. And you see, it's nice because if you look from the fixed camera, you see that the trajectory is a curve. Okay, as if there was a force perpendicular to the velocity of the ball. You see? Like here. And it's the drawing that I've shown you before. In practice, it is. Now this is on the rotating frame, and it's clear. If they launch the ball, you see it goes into that along a curved line. Yeah. And that is the let's say, sort of illustration of the Coriolis force. It's perpendicular to the velocity. Okay, now and now at some point they start to correct, and then okay. This is just rotating in the other direction. You see, it goes in the other way. Okay, then they correct. They correct in advance, and so okay, that's it. It's not really no. And then I want to show this application. This is an animation of the operation of a single axis gyroscope that is used for the stabilization of vehicles. Okay? Traditionally, this has been the first commercial use of MEMS gyroscopes. Okay? Again, it has always been this situation. Not okay. In electronics, the new systems traditionally have been used by the military, and then after some time they move to commercial applications. In later years, the thing already started in commercial applications, and then they moved to consumer markets. But and typically the first type of application is very often in the automotive market, because in the automotive market sensors can be more expensive, and therefore the market is more lucrative. So in this case, of course, for a car, even one single axis accelerometer was could be used for an important function, the so-called ESP, the dynamic control of the vehicle. And this is, for example, the operation of this single-axis gyroscope by Bosch. As I already mentioned, Bosch is the number one producer of MEMS sensors. So this is the gyro. Okay, let me go back a bit. Okay, so this is a single package. In the package you have an acceleration sensor and a yaw rate sensor. Yaw is the rotation along a vertical axis. So this is the yaw. And in the same package you have a yaw rate, so it measures the angular velocity along in the plane perpendicular. No, in the horizontal plane, okay? And the acceleration is the acceleration along the linear direction, okay? Just one axis accelerometer and one axis gyroscope. And then you have also the electronics. It can typically be in the same package or on a separate chip. As of now, it is typically in the same package. Okay, that's it. Now, so these moving things are the two masses. They are excited, and so that they can vibrate in opposite directions. So at any given time, they move in opposite direction with the same velocity and, of course, with the same frequency. They are always in opposite phase. Okay? Let's go slowly. Of course, it is more complicated than the drawing that I've shown to you, but it's exactly the same thing. So